for this very nice. Thank you very much for this very nice introduction. And before I start, I want to show some non-mathematics. So some self-painted paintings. You see some trees which you may find beautiful, maybe not. Here's another tree. But of course, now I should come to. Yeah. Voila. And now we can start with the difficult mathematics. The painting may be interesting if you get find the presentation a bit dry or whatsoever. So what's going to happen today? We speak about the famous Harrington theorem, which is one of the first examples for concrete mathematical incompleteness of the Peano axioms. The Harrington theorem is an extension of a theorem by Ramsey, and I will explain it in a minute. What did we see yesterday? Yesterday we studied a certain property of these Hardy functions, fast-growing functions, and we have shown that the totality of the Hardy functions, when defined through all of epsilon 0, which we characterized by a set E of functions, that the totality of this limiting function is not provably total. That the totality is not provable in Peano's metric, even not in the formal extension Z of Peano's metric, but Z is basically as strong as Peano's metric. Now, what is Harrington about? Well, let us consider the finite Ramsey theorem. Finite Ramsey theorem says for all numbers D, all numbers C, all numbers M, there exists a Ramsey number R. R is big, so big such that for all partitions P, and now we take here what? We take number R and consider R as a set of numbers. R is considered as a set of its predecessors. So R stands for a set of canality R. And then we take the D element subsets of R. So if you set X, then X to the D now denotes set of all subsets of X, such as the canality of Y is equal to D. So for all functions P, or partitions P, from the D subsets of R into a set of canality C, is this C over here, D is this exponent here. For all these partitions, there exists a set H contained in R, such that H is monochromatic, which means the restriction of P to the D subsets of H gives a constant color. And of course, H should not be the empty set. The canality of H should be at least as big as number M. Now, this statement belongs to the world of finite combinatorics and P arithmetic can prove this. Now, Paris Harrington discussed a modification of it. And the Paris Harrington assertion is the following. It starts like standard Ramsey theorem, but now the extra condition is the canality of Y is not only as big as M, but it's at least as big as the maximum of M and the minimum of Y. Now, what we are going to show today is, well, PA does not prove PH. Now, of course, it only makes sense when PH is a true statement. And this can be shown by an appeal to the infinite Ramsey theorem. But today I will just concentrate on the unprovability. Now, what is the goal? You see here, you have numbers D, C, and M, and then you find this R. So R is, and it is taken minimal, a function of D, C, and M. And then basically we show that this function R grows as fast as the lower bound given by the function H index E. Therefore, the Paris Harrington function is not provably total in arithmetic. Therefore, Paris Harrington is not provable. Now, the proof is by magic. The proof has to do with the beauty of ordinals. And you will have problems in figuring out what is going on. So what we do is we start with some basic definitions. We work with the world of ordinals. And only at the last moment, we switch to natural numbers. So we start with an alpha in E. And we write it in a given normal form. So we write alpha as omega to the alpha 1. And then comes omega to the alpha 2. But it could be that alpha 2 is equal to alpha 1. So we collect the terms which are equal together and find a finite factor n1 here. Finally, we had here alpha t times n in east. So this is a version of the Cantor normal form for elements in E. And the requirement here is alpha 1 is bigger than alpha t. And n1 up to nt are numbers at least as big as 1. Every alpha can be written uniquely in this way. And then I say the complexity, the rank of alpha is given by the maximum. Now it's a complexity measure. So what we take into account is the width of this term, which is given by number t, the coefficients n1 to nt, and the complexity of the exponents. And it is understood that the rank of 0 is equal to 0. This rank function has certain properties. They are very elementary, and I will write them on the board. And if finally is time left over, I will also prove them. But it is just an easy verification. So there are 3 assertions. The first one is, well, we need calculation for the rank of members of the fundamental sequence for a given ordinal alpha. So the rank of alpha k is bounded by. Now the fundamental sequence works here at the latest element. So it's bounded by what? The maximum of the rank of alpha. Now, k can be introduced as a factor. So when you have an ordinal omega to the beta plus 1 at k, it's omega to the beta times k. So k can show up as a factor. And of course, the fundamental sequence could add a new term to the right. So the width could be enlarged by 1. And this is then easily proved by induction on the complexity of alpha. If the rank of alpha is smaller than n, then the rank of alpha index n minus 1 is smaller than n plus 1. So this gives a sort of information about when we start with an alpha and step down in the fundamental sequence, what is going to happen with the induced complexities of the elements of the fundamental sequence. And the last element which is needed about the rank of omega mk plus n. Now, what is omega mk? So omega 0 of alpha is alpha, and omega d plus 1 of alpha is omega to the omega d of alpha. So omega d is an omega power of height d, and on top we have an alpha. And the rank of omega to the m k plus n is bounded by n plus 1. If n is not 0 and k is, so this is number 1. And k is strictly smaller than n. Now you see here, these are two terms. So n could be 1, here's a term. This could be 2, so this means that the plus 1 is necessary. But for the rest, it's a sort of easy verification. Okay, now we exploit the power of ordinals. So we define measures to compare ordinal comparisons. So we come to an important definition. Maybe I do it over here. So we assume alpha is uniquely written as omega to the alpha 1 times n1 plus omega to the alpha t nt, with the normal form condition that alpha 1 is bigger than alpha t, and the n1 to nt at least as big as 1. Now we put the ith term in this representation. The eighth summand is given by omega to the alpha I times n of I. So this is a natural definition. Now the exponent in position I is what you would expect is this alpha I. And the coefficient, the ith coefficient of alpha is equal to the number, the coefficient over here. This is for 1 less than equal to I less than equal to t. And if I is different from this interval, then we define it, all these objects to be equal to 0. Okay. Now the next definition is, so what I should say is, in the whole treatment, I follow a workout by Wilfried Buchholz, so I should mention my source. And this is material from his lecture notes from Munich, which is not published. So it is therefore, but it can be downloaded from his web page. Now, Buchholz is referring to a previous paper by Negetre and Löbel, and that is really published in Proceedings of AMS. Now, the idea of the following, I think, goes back to Negetre and Löbel. So we assume that we have two ordinals, alpha and beta. Now, we write down alpha in Cantor normal form, we write down beta in normal form, and then we check when is alpha bigger than beta. And for this, we have to do a lexicographic comparison. So d of alpha beta is, when we compare alpha and beta lexicographically, we write down the Cantor normal forms, and then we compare from the left to the right. So we look for the least I, such that Si of alpha is bigger than Si of beta. So if alpha is bigger than beta, then there will be a position in the corresponding Cantor normal form where the ith term in alpha is bigger than the ith term in beta. Now one defines critical components. K alpha beta. This is K d alpha beta of alpha. And A alpha beta is the critical, when we go into the ith term of alpha, which is bigger than the ith term in beta, and then we go into the exponent of alpha. Well, many definitions, now we need a lemma. And the lemma is easy to prove, but it's absolutely fundamental for the rest. So we assume that we have a triple of ordinals, alpha bigger than beta, bigger than gamma. Now assume two conditions, namely that the distance of alpha beta is less than or equal to the distance of beta and gamma. And moreover, we assume that the coefficient of alpha beta is less than or equal to the coefficient of beta gamma. Then the conclusion is that E alpha beta is bigger than E beta gamma. So you see a very elementary observation, but since it's so important, we give a proof of it. Well, how to prove this? Well, I give a sort of informal proof. So look, what is alpha? Alpha is some Cantor normal form. And now we go into the position E alpha beta, that is a certain I, omega to the alpha I times n of I plus some rest. Now comes beta. You have here d alpha beta, so it means they start with the same terms. And here at position I have a term which is smaller than the corresponding term here. Okay, now there are two cases. One case is the distance here is the same as the distance here. So if d alpha beta is position I is equal to d beta gamma, then this term here has to be bigger than this term here. Now the definition here says this coefficient is not bigger than this one. And the reason why this is bigger than this one can only be that this exponent is bigger than this exponent. And that is written down here. Just easy calculation with Cantor-normal forms. There's nothing hidden here. There's no deep argument. It's just you apply the definition of the order comparison. Now it could be that d alpha beta is I bigger than j, which is d beta gamma. Now, what does this mean? At some later stage, we have here beta j times mj. Okay. And then we know this one is at least as big as this one. What does this mean? This means this exponent cannot be smaller than this exponent. Because if this exponent would be smaller, then the whole term would be smaller than omega to the beta I, and that's not possible. So the argument is alpha I is at least as big as beta I. And now we have this condition on Cantor-normal forms. Let's see, exponents are strictly decreasing. This is bigger than beta j, which is d beta gamma. So beta j is strictly smaller than beta I, and beta I is less than equal to alpha I. Now you see that is easy. Nothing is hidden. No trick involved, just comparison of orders. So you may wonder, how is it possible to do any sort of mathematics with this? Well, I will now continue here on this board. So let it as it is. Now comes the first crucial definition. First crucial definition was the definition of these coefficients, but they have nothing to do with Ramsey theory. Now comes our first partition. We define he. He is working on triples of ordinals. So we take E, 3-element subsets, into a set of cardinality 3. We take 0, 1, 2, but we make formal copies of 0, 1, and 2, just to distinguish these objects from natural numbers. And how is this defined? He, and now we assume that we have 3-element subsets of ordinals. So assume that beta 0 is bigger than beta 1, bigger than beta 2. He of beta 0, beta 1, beta 2 is what? It becomes 0 if the distance d beta 1, beta 2 is smaller than the distance between beta 0 and beta 1. Okay. Now it becomes 1 if this is not the case. And now we compare the coefficients. And case 3 is otherwise. So this is sort of what analytical and Löbel denote as shift graph coloring. Now you can ask, what can you do with this? Well, now comes first interesting observation. We prove a lemma. And this is already quite mysterious. Assume that we have a sequence of ordinals, beta 0 bigger than beta L. L can be as big as possible. Should at least be as big as 2. Now assume that we have number C in our set of 3 elements, such that this sequence here is basically a homogeneous set. But we don't need full homogeneity, we just need some sort of diagonal homogeneity. So we assume that phi of corresponding triples, beta I plus 1, beta I plus 2, they all get the same value. All I less than or equal to L minus 2. Now we want to gather information about how big can this L be? And we want to make this L short. Well, we want finally, what is our plan? Our plan is to produce finally a partition P, which kills this largest condition. We have to make a partition P such that every homogeneous set is short. Now, this is not a partition on natural numbers, but it's a partition on ordinals. But we want to have, if something is homogeneous, that it does not have a large cardinality. Well, the lemma says A, if the color C is either 0 or 1, then L is bounded by the rank of the first term. That's already quite surprising. So the complexity of the first term gives a bound on the cardinality of a homogeneous set. And the second assertion is, if the color C is 2, then we don't know. You have no idea. But the sequence of exponents is a comparison between beta 0, beta 1, beta 1, beta 2, forms a strictly descending sequence of ordinals. Now, you see how the argument works. Either the sequence is short, or we get in the exponents another strictly decreasing sequence. And this is the idea to squeeze out by some sort of recursion. So here could somehow assume by certain induction hypothesis that those numbers, those lengths are short. And this is what we want to obtain. Now we have to prove this. And as I said, today we see just magic. So how is this possible? We put di. It is what? It's the distance between beta I and beta I plus 1. And ki is the corresponding coefficients in beta I and beta I plus 1. Now, what can we say? We want to bound in the rank of beta 0. Now look at the numbers d0 and k0. Now we look back at the definition of the rank function, the complexity function. Now the complexity function bounds the complexities of the exponents and also the widths. So all these i's showing up here are bounded by the rank of R. So both numbers are bounded by the rank of beta 0. Aha. Now, if the color C is 0, what's going to happen? We are in this case. But look, the D function is a distance function. It is just a natural number. So what we obtain is, we obtain a descending sequence of natural numbers. A descending sequence of natural numbers has a property, the length is bounded by the starting term. So if C is 0, then we get D0. D0 is bigger than D1. And now the color is always the same. So bigger than D2. Until we hit DL minus 1. And this number is at least as big as 1. Now we have a descending sequence of natural numbers, length L, where the last term is at least as big as 1. So this means L is less than or equal to D0, and D0 was less than or equal to this number. This means if C is color 0, then this is shown. You see, it just works by itself. No riddle. Well, the riddle is, of course, to come up with this partition. Now, if C is equal to 1, what's going to happen? We now use information about the coefficients. You see, you get a descending sequence of coefficients. So K0 bigger than K1, bigger than KL minus 1, at least as big as 1. Again, this means L is bounded by K0 because we have a descending sequence of natural numbers, L many elements, and the last one is at least as big as 1. So, well, that's great. So assertion A is shown. Now we look into case where C is color 2. And then you see this lemma here shows we are in the case otherwise is a case where these two conditions do not hold. Therefore, these two conditions hold, for every pair of ordinals in the sequence, and therefore we get a descending chain of ordinals over here. So B, then this follows by the lemma. Aha. That's interesting. Now, the magic will continue. So what we have seen now is this specific coloring with triples has some nice properties. Homogeneous sets are either short, meaning the complexity is bounded by the complexity of the first term, or if you have a sequence of ordinals of length L plus 1, then we find a descending sequence of ordinals in the exponents of length L. So the length of this sequence is one shorter. Well, now I wipe out this definition because I just need this part. So we define now a partition on, well, what is here d-element subsets. In our case, we take m plus 1 element subsets. And for this, we define first a set of colors. But this is a technical definition. So what is the technical definition? If I'm working with colorings of dimension 2, I take k many colors. I'll take k plus 1 many colors, 0 to k. And if I take partitions of a higher dimension, then this comes as color class. I take the old color class for a shorter element subsets, union a certain choice of M element. Well, I take a sequence of length M. Now, what is the point? So this class consists of sequence of length M, and by recursion, I have sequence spaces of sequences of length less than M. So these two sets are disjoint. So depending on the choices, when I have M element subsets as a color, then for sure I'm not in this case. Okay, this is a set of colors, and this is finite. This is also finite. The number of colors here is basically, yeah, the geometric sum of the elements is basically 3 to the m plus 1 plus k, but this is not so important for our purposes. Now comes the definition of he m k. And this is now the most important definition of today. So I take an omega power by m, and on top the number k plus 1. And then I take m plus 1 element subsets. So what does this mean? I take elements in E which are smaller than this number. So this one stands for the set of its predecessors. And the coloring goes to CMK. M should be at least as big as 1. And K maybe at least as big as 0. Okay, and this is defined by recursion on M. And now this becomes really magical. So it's not so easy to explain, but first assume that M is equal to 1. Then we have an omega power to the K plus 1. And in our class E, this corresponds to simple polynomials. So that's not too bad. So if M is equal to 1, assume alpha has the form omega to the K and 0 plus 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 omega to the 0 times nk. Now, here I just write down, so alpha is smaller than omega to the K plus 1, identity to the K plus 1, well, it has polynomials of degree bounded less than K, and every polynomial can be written in this way, polynomial with natural number coefficients. And assume that alpha is less than, we assume it's bigger than beta. It has a form, also starts with omega to the K. And here I have coefficients n0 prime plus omega to the 0 times n prime. Okay. So what does this mean when alpha is bigger than beta? There will be in this normal form expressions one position where the coefficient on position I is bigger than corresponding coefficient in beta. So T1k of alpha beta will find the least I such that ni prime is smaller than ni. And the existence of this I follows by the comparison of ordinals. That's all. That's a partition of pairs of numbers smaller than omega to the K plus 1. Alpha and beta have this form. Okay, that's it. Now, case 2 is M is bigger than 1. And what we do is we consider instead of M, we go directly to M plus 1. So let the following. So we assume that omega M plus 1, K plus 1 is bigger than what? Bigger than beta 0. Bigger than beta n. Now we have an M plus 2 tuple. And I want to define what is the value of Tm plus 1k for this decreasing sequence. Well, delta I becomes the exponent of beta I plus 1. And Ci becomes the value of the shift coloring for triples. Okay. Now I define what? E m plus 1 k of beta 0 to beta n. Actually, I want to have a sequence of lengths m plus 2. So I go one element further. So he1 works on pairs. He m plus 1 works on m plus 2 element subsets. So they can be ordered and have a decreasing sequence of elements. And now I define what is the coloring of this one. Well, just look here. If C is 2, then I get a decreasing sequence of exponents. So if, in this case, if C0 is equal to C1 equal to C m minus 1, if this gets value 2, then I'm in this case. And then I can assume that the sequence of delta i's is strictly decreasing. Now the delta i's are exponents in the beta i's. So the delta i's will be smaller than omega index m of k plus 1 and they form a decreasing sequence. So I can apply the previously defined function m of k applied to delta 0 to delta m. So that's somehow magical. And now I'm in the case where this is not going to hold. Well, so in the case of otherwise, well, here in this case, the value of he will be in this set, will therefore be a shorter tuple. Now, if there is some sort of discrepancy, then I just put here tuple of length m, namely C0 to Cm minus 1. This is a tuple of length m consisting of choices of zeros, ones, and twos. Now, this is well defined. By previous lemma. So this lemma, case 2, shows if we are in this case, then the corresponding sequence of exponents is strictly decreasing. The sequence is one shorter and can apply the function which we defined by recursion. Okay, this is a magical coloring. And now, if you have a magical coloring, we want to understand what is this doing. For this, I again clean the board. Well, now assume that we have a homogeneous set for such a coloring. Then we want to know what does this mean. So the lemma is the following. So we have certain side conditions. They are not so important. So one is less than equal to m, less than equal to L, and is strictly less than L. And assume that we have a strictly descending sequence of ordinals, beta 0 bigger than beta L. Assume that this number beta 0 is bounded by omega m plus 1 k plus 1. It's omega m. Okay, and now assume that the sequence of the betas is homogeneous. So assume that we have a color C in C K M, and assume that he K M beta I to beta I plus M. So this is an M plus 1 tuple, which we can apply coloring. This gives value C. For all I less than equal to L minus M. So L minus M because here is I plus M. So L minus M plus M gives the last term. Then something happens. Now what should happen? We want to know that the homogeneous set is small. Then L is smaller than R beta 0 plus M. So this is the pure magic. When we have a very strange coloring, namely this one here, it yields that every homogeneous set is short in the sense that the homogeneous set is basically, well, when we look at descending sequence, when we order this homogeneous set in an order preserving way, that's the largest element, the complexity of the largest element bounds the cardinality of the homogeneous set. So that's the claim. Now, this is far from obvious. There's no way to see this except just studying the proof. Okay, the proof is by induction on M. We do M equal to 1. M equal to 1 is nice. We're in a harmless case, namely we are in this situation where everything is under control. So we write down beta I as omega to the k times ni0 plus omega to the k times ni k. Okay, now we assume that we are in the case m equal to 1, then m is equal to 1 here. Then we are in the case that m is equal to 1 here. Then the xi1 function maps pairs into the first index where these numbers in the comparison are different. Now, what do we have here? We have here that we always have the same color. So we get n0c is bigger than n1c bigger than nlc. Okay, and now again we see we have a descending sequence of natural numbers. This is a sequence of length L plus 1, but the last element, let's say it could be 0. Anyway, does not matter. L will be bounded by N0C. N0C is a coefficient of beta 0. Now here's the definition of our rank function. And we see all the coefficients are part of the rank function. So N0C is bounded by rank beta 0, which is strictly smaller than R beta 0 plus M is 1 plus M. Aha. So this works nicely. Now we have basically 11 o'clock. So I would suggest to make a short break. And after the break, I will continue. But you will see somehow how beautiful the proof is. Just do verification. The proof is difficult to understand. What is the trick with the proof? It's not working out the details. The trick with the proof is coming up with this type of partition and coming up with this type of partition. Now, to be fair, one has to say there is a famous article by Harrington and Soloway in Annals of Mathematics, and they basically started the business of comparing the Harrington function with the fast-growing functions. And well, I don't know how Negetril and Löbel came up with their definition, but Harrington and Soloway have been first in figuring out how to associate ordinates to Harrington. And this is now a refined version of what has been seen before. But okay, now it's 5 minutes break until 5 minutes past 11.
Andreas.
So anyway, so I'm going to prove this lemma. This lemma is about the partition xkm, and I defined xkm last time. It's over here. It's defined by recursion on m, and it's crucially based on a shift graph partition, which is also denoted by xi, but without indices. And this has certain properties, namely homogeneous sets for the shift graph partition are somehow short when the color is 0 or 1, or when the color is 2, we get a descending sequence of exponents in the involved ordinates. Now we really need space. So I will not wipe out this definition. But unfortunately, I have to wipe out this definition. But okay, we assume that this is fine. Okay. Now the argument is extremely delicate in the following sense. Yeah, we have to apply induction. So what we are going to do is we assume we are doing the induction step from m to m plus 1. So what we assume is we take omega tau of height m plus 1 of k, and then a decreasing sequence of ordinals beta 0 to beta L. We assume that m plus 1, of course, less than or equal to L. That's fine. And you have a color C. C is, of course, value of partition he k m plus 1. So C is in C k m plus 1, which is a color for partition he k m plus 1. Now we assume that we have a sort of homogeneity. We assume that he m plus 1 k beta I up to beta I plus m plus 1 always gets the same value. It's value C in this color class for all. Now we have to look when is this last element I plus m plus 1 less than or equal to L. So this holds for all I less than or equal to L minus m minus 1. Aha. Now there are two cases. One case is that the color is in this set, an M tuple, or the color is a tuple of length strictly smaller than M. Let us assume that we are having the case that the color is shorter tuple. So that's case 1. So the color C is not in 0, 1, 2 M tuple over the set 0, 1, 2. Now Ci becomes a value of my shift graph coloring, which just disappeared from the board. Okay. Now one has to be very careful. So this is for all I less than or equal to L plus 2. Now the magic shows up. So we know all these values C are the same. So for I less than or equal to L minus M minus 2, we obtain what? In which case, this is not the case. So the he value, no, stop. We are not in this case because I'm just saying we have not an M tuple. So basically we are in such a case. Anyway, so what? We write down what is he k m plus 1 of beta I plus m plus 1. This is a form I'm a bit confused. So I'm wrong. I was assuming the opposite. Therefore, I was confused. So assume that we are in the case that the color C is an M tuple. I'm sorry for this. So we are in the case that we are not in this case, but in this case. So C is an M tuple having the form Ci up to Ci plus M. Great. I plus M well, he M plus 1 gives an M tuple. So what? I'm now a bit confused with indices, but anyway, it doesn't matter so much. Let's assume that this is the value here is M minus 1. Then we have here an M minus 1. Now we are correct, hopefully. Okay, now we use homogeneity. This is the same as he k m plus 1 beta I plus 1 up to beta I plus m plus 2, which is Ci plus 1 until Ci plus m. And now what does this mean? So these values are the same. Therefore, these tuples are the same. What does this mean? C0 is equal to C1. C1 equal to C2. And all the way, all coordinates are the same. So this means C0 is equal to C1 is equal to C2 until 2 equal to CL plus 2. So that's great. Now we know that if assumed that color C is an M tuple. Now these CIs are either 0, 1, or 2. If the CIs would all have color 2, I would be in this case, but then I would have an element in this function, in this set. But this consists of tuples of length strictly smaller than M. So the case that the color is 2 is excluded. Therefore, color is 0 or 1. Aha. Now you see the C's are the I's are values of the shift graph coloring. They are all the same. The CI's are all the same. And they are either 0 or 1. Therefore, L is bounded by this number. Hence, L is less than equal to the complexity of beta 0, strictly smaller than the complexity of beta 0 plus m plus 1. So this is magical, right? Okay, that was the case that C was coming with this color. Now, the other case is that we are in this case. And for this, I start again on the left-hand side. So, assume C is in CKM. Yeah, how is it possible to go in CKM? It means I have not an M tuple. This means I'm not in this case. So I'm not in this case. Therefore, I'm in this case. This means the CI's have to be the same. And they all have to be equal to 2. So by definition of he k m plus 1, we obtain that C0 is equal to C1 is equal to CL minus 2 is equal to the last number 2. Now we use this observation here. If you have C is equal to 2, you get the descending sequence of exponents, the delta i's over here. So what? You obtain, so the delta i's are these exponents. We obtain omega m k plus 1 bigger than delta 0, bigger than delta L plus L minus 1. Yeah. Okay. Now what do we know? We know that the He values always gives the same color C. So C is the value of He k m plus 1 eta I up to beta I plus m plus 1, I guess. Yeah. It's the same as, now we go into the definition of chi km plus 1 and see it's chi m k of the exponents. Aha. So starting from a homogeneous set or shift homogeneous set of the beta I, we obtain a homogeneous set of exponents for the coloring of index m. And this holds for all I less than equal to L minus m minus 1. Now we can apply the induction hypothesis. The induction hypothesis gives what? Well, what are we going to prove? What we are going to prove is already wiped out. Anyway, I'll write it on the board. The induction hypothesis gives that the length of the sequence, which is one shorter. Induction hypothesis gives L minus 1 is bounded by the complexity of the first exponent in beta 0 plus m. Now we add a plus 1 on both sides. Then number L is less than equal to complexity of delta 0 plus m plus 1. And this is bounded, you see, the rank of delta 0 is an exponent of beta 0. So this is bounded by the rank of beta 0 plus m plus 1. And this has to be shown. So that is magical, right? So I will write down the statement again. So we can now forget about all of this. We just need one nice partition which has the property that homogeneous sets are short. Homogeneous sets of ordinals are short. So I write down the lemma over here, the lemma which we just proved. So we have 1 is less than equal to m less than equal to L. We have a descending sequence of ordinals omega mk plus 1 bigger than beta 0, bigger than beta L. R was in our color class CKM, and PKM of beta I up to beta I plus m was always giving the same color for all I less than equal to L minus m. And then the conclusion was that L is bounded by the complexity, the first ordinal plus m. Okay. Now the question is, what has this to do with the Harrington theorem? That's not even clear yet. We just studied ordinals, partition on ordinals. So it's not even clear that we made any progress. But now comes a proof of. So I remember the definition of a Harrington function. So let's call it pH dCm is the least number R such that for all partitions P from the D subsets of R into set of cardinality C, there exists homogeneous set H contained in R such that H is monochromatic constant, and the cardinality of H is at least as big as the maximum taken over M and the minimum of H. So the Harrington function is the least R such that all partitions have relatively large homogeneous sets. What I'm now claiming is the following. And I take my Hardy function of level omega mk at argument k plus 1. And this is bounded by Harrington function. Now the dimension will be m plus 1. The number of colors is the cardinality of the set CKM. So it is k plus the sum over 3 to the I smaller than m. That's basically k plus 3 to the m. And for the bound of some homogeneous set, I take 2m plus L. Let me check. Two m plus k plus 4. Okay, what is the upshot here? Using the Harrington function, I can dominate this function. Now assume that m is equal to k. Then you get here the diagonal function along all the Hardy functions. And that function is not provably total in p-arithmetic. This function basically dominates the function h epsilon 0. Therefore, this function is not provably total, and therefore Harrington is not provable in PA. Now we want to prove this. And still, we don't see how this works. The only thing what we need is now this lemma. We can forget about the rest. So I wipe out the board. So I start with ordinals. An easy ordinals alpha 0 is omega power of height m k plus number n, and n is m plus k plus 2, but that's not so important. Well, I should make a comment. This bound here is interesting in the following sense. Namely, it also gives independence results of Harrington with a fixed dimension. Namely, these functions, when the omega tower here is bounded, they classify the provably total functions of the fragments of arithmetic. And this also shows when the dimension is fixed, the dimension is 2, for example, Harrington for dimension 2 is not provable in I sigma 1, and Harrington in dimension m+1 is not provable in fragments of arithmetic, where one has induction only for formulas with n quantifiers. So this result is a rather strong result. Now the magic occurs. I have here an ordinal. What can I do with an ordinal? I can consider descending sequences. So alpha I plus 1 comes from alpha I by taking a fundamental sequence. I take I minus m plus 1. Now, what's going to happen? Well, first of all, we eat up the n over here. So the fundamental sequence alpha 1 will just be omega m of k plus n minus 1, then plus n minus 2. Now this n is bigger than m plus 1. So when I is small, I just eat up the numbers which are over here. And at some moment, I hit the number omega mk. So I have a certain weighting procedure involved. And the weighting procedure is given by the number n. And then I start really going down in the ordinals. And the number n will be the least number I, such that alpha I hits 0. So the fundamental sequences go down, go down, go down. And if I did not hit 0, then I step down a further step. But finally, ordinals are don't allow infinite descending sequences. Finally, I will hit 0. Okay. Now, what has this to do with paracering? It's not so clear. Well, what we see is for all I less than n, alpha I did not hit 0. We have alpha I plus 1 is smaller than alpha I. So we get a descending sequence basically of length n. Okay, and what we now do is we jump into our complexity measure, complexity of alpha. We want to figure out what is the complexity of the ordinals alpha I. And for this, I use this lemma here. Namely, basically, the complexity of alpha k is bounded by the complexity of alpha and the index k over here, maybe with a +1. That's not so important. It's important, the complexity of alpha k is one, complexity of alpha and k. That's important. Now, the claim is, well, this is just an easy claim. Technical stuff. For all I less than equal to n, well, then stepping down is just subtracting a 1. Then the complexity of R alpha I is bounded by what? By R alpha I plus m is bounded by a number kappa. And kappa is what? Kappa will be m plus n plus 2. Now, there's nothing special behind this. We take this ordinal here, and basically we subtract step by step this number n over here. And so the complexity is basically given by the complexity of omega mk. And the second one is for all I bigger than n. So n is basically chosen big enough so that the second asymptotics start to work. Then we have the complexity of R alpha I plus m is bounded by I. Yeah. Now, easy to prove, but since it's important, we just do the proof. So assume that I is less than or equal to n, but then, as I said, there's nothing special. R alpha I plus m. Well, if I only subtract a 1, then the complexity will become smaller. So this is bounded by the complexity of R alpha 0 plus m. And now what was the claim? This number plus m is bounded by this number kappa. Kappa is m plus n plus 2, but n is already this number, and n bounds the complexity of omega mk. So this will be smaller than kappa. Well, otherwise, we have to make n slightly bigger, then it will work, right? But this should be true. Okay, now we zoom in into the second assertion. So we assume first that I is again equal to n. What can we say about the complexity of R alpha n plus m? Well, this is bounded by, what is the complexity of this one? Well, it's just the complexity of k, and the whole one, the width of this term, well, there are how many terms? Well, 2. This is also not a problem. So this will be bounded by k plus 1 plus m. Also smaller than n. Meaning this assertion is true for I equal to n. Now, assume by induction that this is true for I. Then, what is the complexity of alpha I plus 1? Well, it's complexity of what? We now take into account what is over here. So this is alpha I of I minus m minus 1. Now we use this lemma over here, which I have not proved, but it's easy to prove. Or I use maybe this one here. This will be bounded by I minus m plus 1. And now if we had an 1, if we had m on both sides, then we see that R alpha I plus 1 plus m is smaller than I plus 1. So nothing has happened here. I just did some calculation, easy calculation. And yes. Well, I first prove this one. That is proved over here. And then I prove this one by induction on I. And I equal to n is the base case of the induction for the second case. And then first I assume that I is equal to n. Then I prove it separately for n. Then in the induction step, I assume that this is true for I at least as big as n. And then I do it for I plus 1. So, well, this is, of course, just technical stuff. And assume that you miscalculate here. There's no need to worry. You can make the number slightly bigger, and then at some moment, these statements should become morally true. Now, what is the basic idea? What one has to take into account? It's basically, if I becomes big enough, then the complexity of alpha I is basically bounded by I. And the reason is I'm stepping down in the fundamental sequence along I, and I have this lemma, namely the complexity of alpha k is bounded by the complexity of alpha and k. Now I have here a slight modification. I have here minus m plus 1. So I can here use an m on the left-hand side, but basically in the fundamental sequence, the index I will be the important one. And after some time, the I becomes bigger, then all the complexity showing up in alpha. And then basically, I controls the complexity of alpha I. Well, now what? The second claim is an easy one. It's a standard claim for Hardy functions. N is at least as big as what? As number h, and h is h omega m k of k plus 1. So what is this? This says the Hardy function measures the length of a descending sequence of ordinals. Here we have a descending sequence of ordinals, namely the alpha I. And the Hardy function is measuring how long such a sequence could be. And still, we don't see the Paris Harrington, right? It's just by magic. Anyway, don't worry, we have 10 minutes left. I should be able to finish within 10 minutes. So, if n is less than or equal to I, less than or equal to capital N, then the following is going to happen. Namely, then H alpha I of I minus m minus 1 is equal to what? Well, the Hardy function, the definition has now disappeared. But I take here H alpha I and plug in this number. So this will be H alpha I plus 1. And Here we have I plus 1 minus m minus 1. And they're all the same. Now h is this number. It is h alpha n. Well, alpha n is subtracting the 1 over here. Of n minus m minus 1. Now all these values are the same. So this is h alpha n, n minus m minus 1. This is 0. N was the first I such that alpha I is equal to 0. So this is equal to n minus m minus 1. This is bounded by n. Aha. That is great. Okay. Now comes it. We claim that this number n, the number n given over here, the number n is counting the steps in the ordinal sequence when we 0. Now this is a natural number. And now we define a partition P on the number n. And we take m plus 1 subsets of n. Now we define the partition P for the Harrington function. And it goes into the cardinality of the set CMK. And I denote this number by R. R is the cardinality of CKM. Now, how is the partition defined? We take an m plus 1 element subsets. I order this in an increasing order. So this is a subset, and I assume that the elements are ordered increasingly. So P of such a subset is given by, well, we are below the number n, and for the number n, we have the corresponding ordinals alpha I. Now I take key m of alpha. Now this is an increasing sequence. So here I take alpha I0, alpha IM. This is now a decreasing sequence of ordinals. Okay. Finally, we have found a partition on natural numbers induced by a partition on ordinals. Now let H be monochromatic for partition P. H, say, has cardinality plus 1. So let us write H in increasing enumeration. then I consider the corresponding set alpha I0 to alpha IL. This is homogeneous for Km. And now the magic comes. If I have a homogeneous set of coordinates for Km, then the canality is bounded is strictly, listen, because the lemma says, now what? The canality of H is equal to L plus 1. And this is bounded by the complexity of alpha I0 plus M. So this L is strictly smaller, then L plus 1 is less than equal to this number. This is plus M. And now we use this claim here. Here I claim strictly less than, or I proved strictly less than. Namely, this number here is smaller than the maximum of kappa and I0, which is the maximum over this kappa and the minimum of H. This means this specific partition P has a property that every homogeneous set is not large with respect to the Harrington condition. The canality of H is strictly smaller than the maximum of a number, depending on input M, and the minimum of H. And that concludes the proof. You see, the proof is completely magical, and it's very difficult to understand. But on Friday, I will show how to improve this. And I will cover Harrington with the largeness condition, where I replace the minimum of H by function of the minimum of H. And to prove the phase transition for Harrington, one has to modify the complicated definition of HMK. So it does not work for that partition. For getting good results on figuring out what will be the phase transition for probability, unprobability in function of F, so that if F is an iterate of a log function, then one needs a better partition. But you have seen today, the partition for today was already quite intricate, and it looks like a mission impossible, but it's possible to improve the presentation of today. But this is going to happen on Friday. Okay, thanks for your attention, and I will stop my presentation right now.